Welcome to This Explainer. If you've ever found yourself wondering exactly how water treatment plants work, well, we're going to explain it with images today. We're completely demystifying the complex, totally hidden science that makes our everyday tap water safe to drink. We just turn on the faucet and expect crystal clear hydration, right? But behind the walls of our homes is this massive, multi-step engineering marvel. Let's explore exactly how it all works. Okay, well, let's dive right into our core question. How does raw, completely untreated river water, which, let's be honest, is full of dirt, debris, and microorganisms, transform into that perfectly safe, crystal clear tap water you drink every single day? Today, we're taking a chronological journey. We'll literally follow a single drop of raw water as it navigates the intense obstacle course of a modern treatment plant. Think of the overall plant layout as our treasure map for today. Starting on the raw water source side, our water drop kicks off its journey by passing through giant intake screens that block large floating debris. Then, it's pushed through an absolute gauntlet of clarification, sedimentation, and filtration before finally being pumped all the way out to the city. We're going to break down every single one of these major zones. Now, what's really wild here is the sheer scale of the microscopic enemies we're fighting. I mean, before we can safely drink this water, we have to strip out an incredibly wide range of impurities. We aren't just filtering out visible dirt. We're dealing with relatively large algae, microscopic bacteria, fungi, giardia cysts, and then zooming way down to tiny submicron viruses and colloids. Simply passing this water through a basic physical sieve? Yeah, that won't work for the tiny stuff. For that, we absolutely need chemistry. Which brings us to phase 1. Clumping the dirt together. To tackle those incredibly stubborn, microscopic suspended particles that just refuse to settle out on their own, our best solution is to literally force them to clump together. The whole process kicks off with a 3-step chemical sequence. First up, the water enters a rapid mix stage. Here, we aggressively mix the water with chemical coagulants, things like aluminum sulfate, ferric sulfate, or ferric chloride. This intense, aggressive mixing step is called coagulation, and it chemically encourages those tiny suspended solids to start attracting each other. Finally, the rapid mixing stops and we ease into flocculation, where we gently mix the water so these growing clumps can casually bump into one another. It's pretty amazing how a coagulant acts kind of like a chemical net. It actually forms a precipitate that physically traps those scattered, free-floating impurities right out of the water. So, the really crucial part is what happens next. During that gentle flocculation mixing phase, it acts almost like a snowball rolling down a hill. As the water slowly swirls around, these sticky particles collide with one another. They bind together to form much larger, much heavier aggregates that engineers call flocks. Basically, we're artificially making the dirt heavy. And here is the beautiful final result of this whole chemical intervention. Because we've forced those tiny, lightweight impurities into massive, heavy flocks, gravity can finally take over. The newly formed clumps become so dense that they just sink straight to the bottom of the tank, pulling all that trapped dirt out of the clean water floating above. Stepping back to a real-world perspective for a second, I really want you to grasp the immense, city-sized scale of urban water treatment. Vast open basins are out there right now undergoing these exact mixing and settling processes. It's literal industrial chemistry operating on an absolutely massive scale, just to keep your city hydrated. Moving right along to phase 2, letting gravity do the work. Once the water has been properly mixed with our coagulants and the flocks have fully formed, the violent mixing stops completely. Flowing from the flash mix and flocculation tanks directly into the massive sedimentation tank, the water is intentionally and drastically slowed down. In this perfectly calm environment, gravity takes the wheel, pulling those heavy flocks right down to the bottom to form a super thick layer of sludge. And that sludge, which consists of all those coagulated colloids and large particles, is routinely removed, dewatered, and disposed of. Meanwhile, the beautifully clarified water at the top gently flows onward. Next up is phase 3, the ultimate sand filter. Clarified water isn't totally pure just yet. So for those super stubborn particles that flat out refuse to settle in the sedimentation tank, we need a crucial physical barrier. The mechanics of these rapid gravity filters are intense, to put it mildly. According to the engineering math, a single square meter of this filter bed is rated to treat a staggering 5,000 liters of water per hour. That's massive. It violently forces the water down through thick layers of sand and media to scrub out the remaining suspended solids and turbidity. But because it traps so much dirt so quickly, the filter clogs up fast. To keep it working, engineers have to frequently clean it by forcing clean water backwards up through the filter, a really cool process called backwashing. But as you might guess, this intense filtration can lead to some huge engineering headaches. Take air binding, for example. As more and more impurities get trapped in the sand, the frictional resistance just shoots up. The initial head loss goes from 15 to 30 meters and just keeps climbing. Eventually, the bottom sand actually acts like a vacuum. It creates negative pressure, which literally pulls dissolved gases right out of the water. These gases form bubbles that stick to the sand grains, seriously messing up the filter's operation. When this happens, no question about it, the filter absolutely must be cleaned. And if that backwashing isn't done properly, well, you get an even worse problem: mud ball formation. If the upward wash just isn't strong enough, mud sinks down into the deeper gravel layers. It sticks to the sand, forming these nasty mud balls that just keep growing in size and number. This completely blocks the upward movement of water during cleaning, causing crazy turbulence and actually displacing the gravel. To fix a severe mud ball infestation, engineers literally have to blast the filter with compressed air for about 4 minutes during the backwash, often supporting the whole ordeal with manual racking and even caustic soda. Let's transition to Phase 4, Advanced Membrane Tech. While traditional sand filters are genuinely remarkable, modern water demands often require even finer filtration. Enter membrane separation. This process essentially forces pre-treated water through a highly specialized barrier under intense pressure. Ultrafiltration, for instance, acts as a microscopic sieve with a porous membrane perfectly sized to rip out larger particles, bacteria, and viruses. But reverse osmosis, or RO, that takes it to a whole other level entirely. It uses such an incredibly dense membrane that it can actually strip dissolved salts right out of the water. The pure water that makes it through to the other side is called the permeate, and it is exceptionally, unbelievably clean. And finally, Phase 5, Disinfection and Safe Delivery. Okay, so we've clumped the dirt, settled it, and filtered it. The water is totally clear. But before it reaches your home, we absolutely must ensure nothing living is left in it. This brings us to the crucial role of chlorine in the disinfection phase. Interestingly, chlorine isn't just dumped in at the very end. It's actually often added earlier, during sedimentation and filtration, to prevent microbial growth inside the plant tanks themselves. It acts as a powerful oxidizing agent to kill harmful pathogens. But honestly, its most important job is what we call residual disinfection. It lingers in the water, providing this invisible shield of chemical protection as the water travels miles and miles through dark, underground municipal pipes. Looking at the big picture one last time, the perfectly purified, fully disinfected water flows into a massive storage tank called the clear well. From there, the high-lift pump kicks in, pressurizing the water and blasting it out into the vast municipal distribution system, that incredible network of pipes leading directly to your neighborhood. The journey of a single drop of water from a muddy river to your glass relies on complex chemistry, gravity-defying physics, microscopic filters, and precise disinfection. It's an absolutely incredible daily achievement. So, what hidden engineering miracles will you think about the next time you casually turn on your tap? Thanks for joining me on this explainer, and keep questioning how the world around you actually works.